Hi everybody, I hope this is going to help out for our quiz or our exam tomorrow. I'm just going to do some selected problems. I don't think it's necessary to do all 15. So I'd focus your studying on these, just make sure you know how to do things like this. First one is going to be during the Apollo moon landing, reflecting planets were placed on the moon. This allowed Earth-based astronomers to shoot laser beams at the moon's surface to determine the distance. Reflected beam was observed 2.52 seconds after the laser pulse was sent. The speed of light is 3 times 10 to the 8th. That's actually, I just couldn't make it, but 10 to the 8th meters per second. What's the difference between the astronomers and the moon? So you got to think about this as we've got the Earth here and we got the moon here. And it took 2.52 seconds for the laser, the light, to go to the moon and then back to the Earth. So we got to remember a couple things. First off, the speed of light doesn't change. So we know the velocity is 3 times 10 to the 8th meters per second. Sorry about that. And we also know the time total was 2.52 seconds, but we're looking for the distance between the Earth and the moon, not the distance from the Earth to the moon back to the Earth. So we have to take this time and we're going to divide it in half. So instead of 2.52 seconds, it's going to be 1.76 seconds, I think. Let me double check that. 2.52 divided by 2. Yeah, I'm sorry, 1.26, not 1.76. So 1.26 seconds. And the displacement, the distance, that's what we're looking for. So again, there's no change in velocity for the speed of light, so we can use v equals d over t to find our velocity, or to find our displacement. 3 times 10 to the 8th meters per second equals the displacement, which is what we're looking for, over 1.26 seconds. That's our time. We can put this over 1 and we can just cross multiply. So d equals 1.26 seconds times 3 times 10 to the 8th meters per second, and the seconds will cancel out and we're left with meters, and the displacement will be, hold on, 1.26 times 3e8, that should be a big number, 378 with 6 zeros afterwards. 1, 2, 3, 4, 5, 6. So 378 million meters away. So again, that's a v equals d over t, no accelerated motion, and that's how you do A1. A2, same basic deal. We've got a falcon and clock driving down at a speed, a constant vertical velocity. These are the big words right there. Constant vertical velocity of 97.2 meters per second. So we know that it's flying downwards. Where's my eraser? Is that an eraser? That's the eraser. So, you know, this is kind of, again, kind of open and shut here. We know the velocity is 97.2 meters per second. Falcon dives down from a height of 125 meters. So that's going to be what's happened, like that's the distance it's going, but we actually care about the fact that it's negative 125 meters and it's negative 97.2 because the Falcon's flying downwards and the Falcon is moving downwards. So the question is, how much time does it give? That's your displacement. So we're looking for time for the rabbit to move or not move. We're going to use the same equation, v equals d over t. Negative 97.2 meters per second equals the displacement, which is negative 125 over time. Multiply both sides by time, you get negative 97.2 t equals negative 125. And then we're going to divide both sides by negative 97.2. Negative 97.2. We should end up with a t of 1.03 seconds. Moving on to our next one, I figure we can skip ahead because the next couple were a little onerous, and just in the interest of time and you guys being efficient in your studying, just skip up to number 7. We're dealing with something that's actually slowing down, which means we have an acceleration. That looks like a G. It's supposed to be an A. Oh, these tablets. Acceleration. There you go. The second we have an acceleration, now we have to start making our VI, VF, A, T, D chart. So we have to sort of decipher what's going on in this text. A caterpillar crawling up a leaf slows from 0.75, so the initial velocity is 0.75, to 0.5, so that's going to be the final meters per second. So both these are meters per second, at a rate of negative 0.05 centimeters per second squared. Actually, that's a typo. I copied that wrong. Actually, I'm sorry. All of these are not exactly. This should be centimeters. When I copied it wrong, when I copied it, guys, I just didn't copy it correctly. There we go. So now we're back in business. 0.75 centimeters per second to 0.5 centimeters per second at a rate of negative 0.05 centimeters per second squared. The fact these are all centimeters, we don't have to convert them because they're all going to cancel out, and I'm not going to give you too much in the way of conversions on the quiz. So the acceleration is negative 0.05 meters per second squared. How long does it take to make the change? So we're looking for the time. The displacement doesn't matter to us, so we need to use the equation that's got a VF, a VI, and an AT, which I figure VF equals VI plus AT. So the final velocity is going to be 0.5 equals 0.75 plus negative 0.05 t, and we're going to have to subtract 0.75 from both sides. So we'll end up with a negative 0.25 equals negative 0.05 t. And we're going to have to divide both sides in order to isolate t by 0.05 negative, 0.05 negative. And that will cancel those out, so we'll end up with a time that is two negatives divided by each other, give us positive numbers, and 0.25 over 0.05 gives us 5 seconds. So time is 5 seconds. There's your answer. Hope that helped. Next. The Wizard of Oz. Dorothy awakens in Munchkinland. We've talked about this before. First off, we're dealing with a height. We've got a height. We know it falls 3,000 meters, and that's really all that we know. But we actually know a lot more. It's just a matter of can you sort of infer what's happening? So we've got this house, and it's floating up from a tornado. And last time I checked, when anything flies up and then is allowed to fall down, between the going up and the coming down, we actually come to a rest. So the initial velocity up there, 3,000 meters high, is going to be 0 meters per second. And what we're looking for is the final velocity there. The acceleration is going to be negative 9.8. Negative 9.8 meters per second squared. Negative 9.8 meters per second squared. Time, they don't tell us anything about it. They don't give it to us. But we do know the displacement. So that time doesn't really matter. But the displacement, we know it's 3,000 meters. But we also know that the house is falling. So the house actually travels negative 3,000 meters down in the vertical direction. So now we can use our physics. We can use some kinematic equations. We're looking for one that's got a VI, a VF, an A, and a D. And for my money, I'd say the best one to use is going to be VF squared equals VI squared plus 2AD. That's going to be VF squared, because we don't know that, but 0 squared plus 2 times negative 9.8 times negative 3,000. Now I got to do some plugging in. 2 times negative 9.8 times negative 3,000 should give us a VF squared of 5,880. 58,800 meters squared per second squared. Don't worry about this because we're going to take square root of both sides because I don't want VF squared, I want VF, and these things are we're gonna take the square root of the meter squared per second squared, and that's gonna end up with meters per second. So all we have to do is plug in on the calculator, what is the square root of 58,800? And we should end up with 242.48 meters per second. But this is the square root, which means it's plus or minus. And the fact that the house is falling, we can get rid of the positive one, and it's going to be negative 242.48 meters per second. Hope that helps. Next. No, delete that. So that was 8. Let's go to 9. The Tambora volcano in the island of Sumbawa, Indonesia, has been known to throw its ash into the air at a speed of 625 meters per second during an eruption. How high could this plume have risen? So again, we're shooting something up. We're dealing with a projectile now. So we know the acceleration is negative 9.8 because it's something that's getting thrown up. Here's the crazy thing. We want to know the displacement. They don't mention time, so I'm not even going to bother with it. And they tell us it throws the ash into the air with a speed of 625. So that's a positive 625 meters per second. My question to you is, how fast is this stuff going when it gets to its highest place? The answer is it stops. You're talking about something that's going up and then it comes down, but in the middle, between the up and the down, it's got to stop. So that's how I know my final velocity is going to be 0 meters per second. Again, we got a d, a vi, a vf, and an a, so I think the proper equation is going to be vf squared equals vi squared plus 2ad. So that'll be 0 equals 625 squared. This is going to be a big number, plus 2 times negative 9.8 times d. So we're just going to do a little bit of math on the calculator. 625 squared, that is going to be a ridiculously big number. 390,625 plus 2 times negative 9.8 d, but you know what, I'm going to save us all some trouble. 2 times 9.8 negative is going to be negative 19.6. So I'm going to 390,625 plus negative 19.6 d equals 0. So now the question is, what do we do? We're looking for d, and we got a negative 19.6 times d. We got to get rid of this 390,625. To do that, we're going to subtract it from both sides. 390,625. So that's going to cancel out, and we're going to be left with 0 minus 390,625. So we'll end up with negative 390,625 equals negative 19.6d. And then what do we do next? We divide both sides by negative 19.6. 19.6. Do the magic of smart software. Voila. We get to come down here. So let's do some calculations. 390,625 divided by 19.6. So we end up with the negatives canceling out. That goes away. The d is 19,929 and change 0.84 meters. So the crazy thing is these all become positive, and it should make sense because last time I checked, we're talking about a volcano. It's going to shoot that ash upwards. So that's going to be the positive height. Cool beans. Hope that helped. Let's look at another one. 10. I don't have very many for us to deal with. I want you to be efficient when you're studying. So I've got 10. I've only got 2 more after this, so there you go. Let's hide this. All right, Shipuli, the jungle dweller, is out hunting for dinner when, sorry about a typo, a coconut falls from a tree and lands on his toe. The nut fell 1.4 seconds. How fast is it going when it hits his toe? Really doesn't like there's a lot of information here, but again, if we've been paying attention, we know we're dealing with accelerated motion because it falls from a tree. And when a coconut starts in a tree, the initial velocity is 0, and we're looking for how fast it's going when it ends. And if we're looking for that, we can make the assumption that there's some sort of acceleration. And you know that as a coconut falling off a tree, we're talking about a projectile, so the acceleration is going to be negative 9.8 meters per second squared. The time they give us is 1.4 seconds, and the displacement is going to be sort of disappeared because we don't know it, we don't care about it, they don't give it to us, so don't worry about it. VI, VF, A, and T, the equation I would use would be VF equals VI plus AT. So we're looking for the VF equals, the VI is 0 plus negative 9.8 T, but we know T, which is 1.4. So a little bit of mathematical magic for you. 9.8 times 1.4 should be negative 0 plus a negative 13.72. And that is your VF, which is basically what we're looking for, VF. And the 0 goes away, so VF shall be negative 13.72 meters per second. And this is interesting again. You negative 9.8 gives you a negative 13.72, and that just means that we're falling down. So I hope that helps. Next. I'm going to do this one. It's a couple of different layers to it, but we spoke about it in class. While repairing a defective radio tower located 410 meters up, Lyle drops a hammer, falls all the way to the ground below. So A and B are dealing with the whole fall down. C is dealing with less than the whole fall down, so we'll deal with that in a second. But VI, VF, A, T, D, again, we're dealing with a projectile, which means there's acceleration of negative 9.8 meters per second squared. The initial velocity for something we're dropping is going to be 0. We want to know the time as well as the final velocity. And we know it's going to fall 410 meters, so the displacement will be negative 410 meters. So the first thing we can look for, we can do what do you want to do? Let's solve for the final velocity first. I think that'll be the easier of the two. VF squared equals VI squared plus 2AD. So the VF is what we're looking for, equals 0 squared plus 2 times negative 9.8 times negative 410. Negative 410. I hope you can read that. Let's see here. 2 times negative 9.8 times negative 410 should give us a VF squared of positive, interestingly, 8036. And we don't want that. We want the square root of it. And the good news is we have a positive number, so we can take the square root. So VF should be a positive or a negative square root of 8036. So let's see what that is. The square root of 8036 is 89 meters per second squared. 89.6 meters per second. Sorry, not meters per second squared, just meters per second. And the VF is, because it's falling down, is going to be the negative 89.6 meters per second. So hope that piece helped. 89.6 negative. And now you can go ahead and figure out the time. And I dare I say the easiest way to do that is going to be VF equals VI plus AT. The VF is going to be negative 89.6 equals VI, which is 0, plus negative 9.8 times T. So let's do a little bit of math. We'll clean this up a little bit. Negative 89.6 equals negative 9.8 T. And now we can do the math, so it's easy. So I just got rid of the 0 here to clean it up a little bit. Negative 89.6 divided by, because we have to solve, Divide by negative 9.8. Divide by negative 9.8. Divided by negative 9.8. Should be about 9.14 seconds. I hope that's what we got in class. To me, it seems a little small, but I just looked at the work that we did and it looks good. So, yeah, hope that was good. 9.14 seconds. And again, positive time. We can't go back in time. That's kind of a little trick to check yourself with. You know, we had two negative numbers here, and we should have because we needed a positive time. So then the next question is, well, that's cool. What about this 1.5 second deal? Well, it's the same basic story of what's happening. VI, VF, ATD. The only thing we're changing is the time. So instead of allowing it to fall for all 9.14 seconds, we're only allowing it to fall for 1.5 seconds. We got that out of the problem right there, 1.5 seconds. So the VI was still 0 when he dropped it. The acceleration is still negative 9.8 meters per second squared. We just want to know how far will the hammer have fallen, so we're going to look for the D. So we got a VI and A. The VF is irrelevant. VI, A, T, and D. I would say D equals VI T plus 1/2 AT squared. It's going to be your best bet. D equals 0 times T. And I don't care that the T is 1.5 because 0 times it is going to still be 0. Plus 1/2 times negative 9.8 times 1.5 squared. So then we just do a little calculation here. 1/2 times negative 9.8 times 1.5 squared should give us a D of negative 11.025 meters, which means that hammer dropped just over 11 meters down. So there you go. Hope that helped. We can go on to the last question. Perhaps sometime in the future, and this is reminiscent of bleacher ball, which you did. So we gave you a lab on it. We gave you. I'm giving you a problem on it. You should probably expect something like this on the exam. We're dealing with something that is accelerating again, but this time we're on a different planet, so we don't know the acceleration of it. So why are you not working, pen? Yes, pen. Hold on. I have no idea what happened, but it just took me like 10 minutes to fix this. But no time passed for you, so that's good. So anyway, we're again dealing with a projectile, which means we're going to have VI, VF, A, T, D, and you don't know what the A is. So we have to resist the temptation to plug in negative 9.8 for that acceleration. That's what we're looking for. But not much else changes. You know the initial velocity of something you drop is going to be 0 meters per second. You know that it takes 0.68 seconds to fall, and it falls negative 0.9 meters. So this is actually a pretty open and shut thing. We don't have a final velocity, so we don't care about it. VI, A, T, and D, I think we're going to be able to use D equals VIT plus 1/2 AT squared. So negative 0.9 equals 0 times 0.68, but that's still going to be 0, plus 1/2 A 0.68 squared. So now here's the little problem that we're going to have. We're going to have to do a little bit of mathematical magic here. I'm just going to sort of loop these all in together. 1/2 times 0.68 squared, so 0.68 squared equals 0.624 times 1/2 is going to be 0.2312 A. So I multiplied this times itself, 0.68 squared, and then multiplied this whole thing by 1/2, and I got 0.2312. Now I get to isolate A, 0.2312. I'm going to divide both sides by 0.2312. Interestingly enough, it's a positive. Okay, so that's really important that we keep the positives. These two go away. My acceleration is going to be negative 0.9 divided by positive 0.2312. 0.9 divided by 0.2312. And we should end up with a negative 3.89 meters per second squared. So there's your acceleration due to gravity on Mars, complete with its negative acceleration because it's a vector quantity, and that means it's accelerating down. So I hope that helped. And then blank sheet here, so let me just sort of give you a couple other things to ponder. We talked about displacement versus time, and anything that goes positive slope is a positive constant velocity. If you're dealing with a flat line, that means the velocity is 0, and then we're dealing with negatives, that means it's a negative constant velocity, and then we come back to a rest. And then if we have a curvy line, now we're dealing with an acceleration, and the fact that it's opening is up is positive acceleration. So you may want to go back in your notes and look at this. Same deal with a velocity versus time graph, positive velocity, negative velocity, and zero velocity. So anything that touches this line is going to be stopped. Anything that's above the zero line is going to be a positive velocity. So if we have a flat line there, that's as flat as I can make it. That's going to be a constant positive velocity. And then let's say it stops, so that's going to be a velocity of 0. Then we drop down here, that would be a constant negative velocity because we're again dealing with a velocity that's not changing. And then anytime you see, sorry guys, my drawing is not great on my little tablet here. There. Then anytime you see something that might be a sloped line, now we're dealing with a changing velocity or an acceleration. And if we're changing the velocity away from the zero line, getting further away from it up here, we are speeding up, and if we are getting closer towards it, we are slowing down. So that's kind of it. I just kind of remember that positive velocity is towards the right or up, and negative velocity is towards the left or down, and same thing with positive and negative acceleration. So I hope I didn't take too much of your time. That was just under a half hour. I hope that helped, and good luck with your studies for the test tomorrow.